Hi everyone, my name is Wayne. I work at the R&D department at Unity in sunny Copenhagen here. And today I want to talk about DSPGraph. Well, I've only got 20 minutes or so I just want to get straight into it, and I'm really only going to give a kind of a top-level overview of why it exists and kind of where we're going with it at Unity, because any sort of deep dive would take too long. So what is DSPGraph? It's Unity's new digital signal processing technology. Okay, so digital signal processing, we're going to get into what that is, but the reason why we're calling it DSPGraph is because it's all about signal processing. I did a talk last year on DSPGraph actually, so if you guys want to kind of get a bit of a deeper dive into this, you can watch this talk. It also goes into how we did the audio for Megacity, which is a demo you can actually see over at the kiosks over there. And as I said, we're going to start from the basics. We're only going to give a cursory overview of kind of what's going on. So I want to start with the bare minimum. What is digital signal? Okay, so a digital signal. So it's about sampling a waveform, like for example, an audio waveform, at regular intervals. Okay, so when you digitize an audio signal, you sample it regularly, and then you can reconstruct the waveform at a later time. For example, when you want to send it to the speakers at a sound card. Let's take an arbitrary a signal sampled at some sort of rate, and the way we store that in computers is that we just have a float buffer array usually. I mean, you can also, if you don't know what a float is, then this talk may be a bit difficult, but if you do know what a float is, we generally store them in buffers of floats representing the values of each of these digital samples. So easy. But what about signal manipulation? This is something that you kind of actually want to do regularly in a game engine, okay? A game engine is a dynamic, real-time kind of thing happening consistently. So you want to do some digital signal manipulation. I'm going to give a couple of really basic examples of digital signal manipulation. So imagine if we have two arbitrary waveforms here, and what we want to do is combine them into one. So simply you just add the two numbers together and you get an output waveform, and this is called mixing. Very simple, okay? And what you can also do with digital signal processing is you can, for example, maybe have a large buffer where you actually take a digital signal and you store that digital signal somewhere in the future of that buffer, okay? So maybe you put it some distance in the future, and then you read from the past in that buffer and put it into the output. And then you update the read and the write positions. So this is a very simple operation that you can do, but what you actually have here is a way of delaying the sound that comes from a sound source. So if I play a sound, I can actually delay how long it takes to get to the speakers, which is pretty cool. And what that means, and this is called a delay line, usually. And what we could do, for example, with this very simple digital signal processing is model the speed of sound of air through air by the distance to the source from the listener. And so already we're starting to be able to build realistic behaviors and model a 3D space. And I put this little GIF here because it's the only way I could visually represent the speed of sound. You can see the pressure wave of the sound front through the air. Okay, so signal processing. It's important in games. It's allowing us to model, real-time game mechanics, which is obviously an important aspect of an interactive experience, okay? Some of the other things you can do is you can resample. So resampling is about pitching it up and down, and that means we can do some approximate Doppler characteristics. We could also reverb, so we could model the echo of a physical environment with some reverb. We could add some low pass to model a source going behind another object and being occluded. And we can actually do all sorts of procedural generation as well. So we could actually create sound from nothing. We can model things like wind, car engines, and other cool things. So there's this is a rabbit hole of interesting stuff you can do with procedural sounds. Usually when you have DSP and you're doing these different signal manipulations, you assemble them in a chain. So you do some delay, and then you maybe add a reverb, maybe you do something else, and you chain them up into a graph. This is the other part of the DSPGraph nomenclature. And so you pass the signal from one DSP unit to the other, until eventually you hear it in the sound card, or from your speakers, sorry. And if I put this into the bigger picture of an audio engine, an audio engine in a game engine, you can imagine that you've got a whole bunch of different things playing, like footsteps and dialogue and stuff like that, which play into the DSP. That DSP does some real-time manipulation based on what's happening in the game. And that manipulation is coming from gameplay automation and gameplay logic. So imagine that parameters are defining, for example, the distance between the source and the listener in real time, and increasing or shrinking the delay line that we talked about earlier. So it's about real-time DSP, and you need to do it at real time because the game is a dynamic experience. Okay, it reacts to user input. It has to be high performance because we need to feed samples to the sound card at a high rate, and I'll get into that in a second. And it has to be low latency. So when something happens, we want to be able to hear that kind of instantly from the speakers. So in most computers these days, we have two important threads for an audio system, the main thread and the audio thread. The main thread is about where we decide things, where we decide the distance between two things, for example. And the audio thread is where we actually produce the samples, where we produce the sound for the sound card. And it's usually on another thread because it has to be super snappy, it has to be constantly being able to provide the sound card with new samples, because it's such a high priority. If you drop a frame of audio, then you get sort of really jarring stutters in your audio playback. Okay, so the main thread is making changes, and to do that, you generally want to have a command buffer. So you want to send things, you want to send instructions over to the audio thread to make changes, like parameter automation. You want to increase and decrease that value. You want to create DSP on the fly and destroy it. You want to make topological changes and change the volume, things like that. And if you do that, and you do it right, you kind of want to do it in a very lockless way. So you don't want to have the main thread and the audio thread waiting on each other. You want to do it atomically. So if I want to do a bunch of different changes, you want to do it at once. You don't want to go through halfway through the changes and then realize, and then the audio thread picks that up and says, okay, I'm going to do this half, and then you're in some limbo state. It has to be low latency, of course, and sample accurate. So if I want to make a parameter automation at this sample in the future, it has to be kind of addressable in that kind of level. So, talking about samples, the way it usually works in an audio thread is you get a callback from the computer, from the operating system, regularly, and it says, hey, how about some more of those samples, eh? And those samples are usually asked for in, it depends, but usually you're asking around 1,024 samples per mix. So per every callback, it says, give me 1,024 samples. And you actually, generally speaking, at least 44 to 48,000 samples per second. This is so, let's not get into that. But that's generally about 47 callbacks per second, which is about 21 milliseconds of audio for every callback. So very snappy, very kind of responsive audio to the operating system. The way you classically do that is you take your graph that you saw before and you flatten it out. So you can always take a graph and flatten it out in terms of dependency order. You do that DSP one after another, passing the buffers from one to the next, and eventually, after you're done, you pass off that buffer to the operating system. And you can imagine that, and this happens, for every frame, a new mix. And you can see that, like, as you do more and more DSP, you're actually encroaching on the next callback, which means that you could, in fact, not provide samples to the sound card in time, and then you start getting hitches. So you can overcome this by, you could, in modern computers, you have multiple cores now, which is really great. So you could probably share that DSP work over multiple cores. And if you do that and you flatten the graph and then you put the appropriate jobs on the appropriate threads, then you can actually get a shorter wall time. So the physical time it takes to mix is shorter, and you're able to provide samples to the sound card in a snappy way, which means you can do more work, more interesting things across more cores. So that's a good deal. You can also do interesting things like, when we have to provide samples to the sound card, maybe we just give them give the sound card a pre-mixed buffer, and then launch jobs at the end of the frame that are going to be finished by the time you get to the next frame. And then you just take the results of that, give it to the sound card, launch some new jobs. And it means that your actual wall time on the audio thread is next to nothing, and you can do a lot of work in between. So this is when you can start doing really interesting things in terms of audio, but it adds latency. So it's going to add like 21 milliseconds of latency because of that frame delay. Okay, so that's, I guess, how sound is generally working in a computer. And in Unity, we have this cool thing called the C# job system, which I hope you guys have kind of got across throughout Unite here. And we talked about jobs in the previous thread. So at Unity, we thought, okay, so what if we took that C# job system and kind of extended it and mixed it up a bit and maybe, made our own version of it, okay? So what if we had our own types of jobs with our own types of parameters, okay? And that's what that execution context is all about. Our own stuff, our audio things in these jobs. And I'm not going to show any more code than that because we don't have time for it, but I'm going to describe it. So generally speaking, in these audio kernels, you are executing. You have to take the buffers from the input, and they can be any number of different inputs depending on what DSP you're actually writing. You have to use the parameters to define whatever you're doing with those buffers in terms of DSP, and then you have to fill out the outputs. So these are the kind of characteristics of an audio kernel. You can have multiple buffers coming from all different DSPs mixed together for every input, and you can take the output buffer from each DSP and connect it to multiple other DSPs. And as I said before, you have gameplay logic and automation which is controlling these parameters from another thread via this lockless command buffer mechanism. So, C# audio engine, pretty crazy, but very interesting. It's something that is massively customizable, extensible, cross-platform. You just write C# code and it compiles for all platforms as usual. And there's a lot of, it's very fast in iteration. So we can actually just type the code in Writer, tab back to Unity, and lo and behold, you've got a new DSP, which is rapid iteration on such a low-level concept as DSP. But what about performance? So we all know that C# can have its performance quirks, like GC garbage collection can come along, stall all the threads. Now we're in trouble. We can't provide those samples to the sound card in time. We get audio hitches. And that's something that a lot of you guys have probably seen on audio filter read, which has been the bane of our existence for a long time. But we have this other technology at Unity which we're leveraging. So the C# burst compiler. So we take C# code or high performance C# code and we do really cool things with it. We do all sorts of auto vectorization, we do all sorts of like other performance optimizations and stuff like that. It's cross-platform, and in the future, because we're in control of the compiler, we could do interesting things with other coprocessors on the machine. So maybe not just CPU we can target in the future in terms of being able to execute these audio kernels. So we put the burst compile flag on the audio job, and yes, we have performance by default, which is great. And this is what DSPGraph is. Okay, so nothing more, nothing less. It is a low-level API layer for audio DSP programmers. It is meant to serve as the foundation of everything we do audio-wise at Unity, and it is meant to be as high performance and as scalable as you can possibly get. And that's why we built it, and that's why I'm here right now, basically. It's user-land, it's obviously extensible and customizable, and it's something that you guys can reach into if you want to. But this level of abstraction, such a low level of abstraction, is not for everybody. It's not for, it's not, you know, I haven't talked in concepts that you're used to, like listener, source, you know, audio clip, those sorts of things. It's a very low level thing, but we made it available to everybody so that, well, we could build an engine on top of it, number one, and allows anybody who wants to build an engine on top of it if they want, but also they can just dip in where they need, write a DSP for X, or whatever you kind of need to solve your problems. We never want to say to you anymore like, oh, you can't do that in Unity. It's just a kind of how far you want to reach down into it. So that's what DSPGraph's all about. Like I said, it's not for everybody. So what I want to talk about for the last 5 minutes is what we're doing next and where we're heading. So I've got this nice little picture which I got from the roadmap talk, and it kind of describes what we're doing here, where DSPGraph is a foundational level of API for us and for you as users. On top of that, we're working hard on a new DOTS audio engine. So we're going to be writing a new audio system on top of DSPGraph for DOTS. And we're also starting to prototype, and we're going to push hard, obviously, artist tooling. Artists are important, and it's something we need to address and do service to. And we're starting on that very soon. So some of the things we're doing. DOTS audio, new audio system. It's expressing all the concepts that you actually want to use day to day. Things like listeners, multiple listeners, sources, voice playback, spatialization, audio clips. These sorts of things that you're used to kind of using. This is what we're working on right now. It's built on DSPGraph, so it's going to be good in terms of performance. It's scalable. It's going to be a package, of course, so you guys will be able to reach in and see what's going on, make changes. You're not going to be blocked. Again, we don't want to say you can't do this at Unity. It just depends on how much you want to reach down into it. And it's production driven, so we're actually, building this in the context of our own internal productions. So we're trying to harden the things that we build against real world use cases. Artist tooling. So this is actually a picture of a composition tool for animation, but this is kind of what we're working on under the hood. prototyping right now, but this is actually going to be a tool for not just animation, it's going to be for audio and video and other subsystems where we can assemble behaviors from a bunch of like atomic nodes doing something, hooking up parameters from the game logic and other things, and having the data flow or the sound, the signal, being you're able to construct these graphs visually. So it means that it's going to allow artists to build very complex behaviors without having to write a single line of code. It's going to be built with the visual scripting framework that we're also working on right now. So these things are going to play very nicely together in terms of being able to define data flow behaviors, leverage some visual scripting in there as well, and build a kind of very complex behaviors without having to write any code at all. And we're also working on something which I mention this because it may interest some people. We're also working on a new hardware abstraction layer. So I talked about the sound card before, about sending samples out to the sound card. And classically in Unity, that's been kind of very, you don't get much options in terms of that. You can only acquire a default device and then output to that device. So what we're doing is we're changing that completely. We are allowing users to kind of acquire output devices freely and send signal to any sound card that you have on the machine. So if you have 20 different USB headsets connected, you'll be able to address each one individually. It's going to be super flexible. It's going to be a package, so you guys can reach in, see how it works, build on it. And yeah, it's going to be our new method of outputting audio to the sound card. So, and we hope that it'll allow you guys to kind of express the kind of output needs that you have. So that's DSPGraph. That's what we're doing in audio. We're trying really hard to get this done as quick as we can. And yeah, thank you very much.